Hi, I'm Rocco Servedio. I'm going to be talking to you about deterministic approximate counting of polynomial threshold functions. This is joint work with Liang Tan, and let's get started. So this is a talk about deterministic approximate counting. Just to remind everybody of the basic problem formulation, this is a problem defined by a class of Boolean circuits. Pick your favorite class. A deterministic approximate counting algorithm is a deterministic algorithm. You give it as input a function, a circuit belonging to the class, and what does it do? It deterministically comes up with an approximation of the number of satisfying assignments, or we should say the fraction of satisfying assignments additively accurate to plus minus epsilon. So just like the figure indicates. Why do we want to do deterministic approximate counting? Well, this is a disguise for the problem of figuring out whether or not P equals BPP. If we have a deterministic approximate counter for the class of all poly-size circuits, we get that P equals BPP. That's almost the definition of the problem. That would be great, but of course this is beyond the current state of the art. So given that, what do? Well, it's a program kind of like circuit complexity. We try to prove restricted lower bounds for the classes that we can handle. In circuit complexity, here we try to do deterministic approximate counting for different restricted classes. And I've shown you some kind of combinatorially defined concept classes or function classes on the left, DNFs and CNFs. Over on the right, we have some geometrically defined classes, intersections of half spaces, and the focus of this work will be polynomial threshold functions, and we'll have pictures of them soon. Okay, so this probably reminds you of pseudorandom generators. What's the connection with PRGs? Well, a natural way to do deterministic approximate counting is to construct a PRG for your class of functions. What is a PRG? It's just an efficient, again, deterministic algorithm that expands sort of a short truly random seed, that's like this R-bit truly random seed here. The PRG takes it in as input and spits out an N-bit pseudo-random seed. Right? And the property of that pseudorandom seed, the thing that makes a PRG, is that it fools every function in the class. In other words, if you were to feed in a truly random n-bit string to the function f in the class versus a pseudo-random output of a generator, the circuit in the class, by definition of being a PRG, can't tell the difference. It's equally likely up to some epsilon error to accept a truly random input versus a pseudo-random input. Okay. So with this definition of PRGs, again, probably familiar to most of you in hand, it's clear that if you have a PRG for a circuit class, that gives you a deterministic approximate counter. Why? Because you can just enumerate over all the possible seeds to the PRG and keep track of how often it's outputting 0 and 1, and this will give you the right answer. So you can certainly solve deterministic approximate counting if you have a PRG for a class, but you may be doing too much work if your only goal is to do deterministic approximate counting. PRGs are solving a harder problem in two senses. One sense is that they don't really look at the input. They just use it as a black box, right? They feed in this input and get out a 0, 1 value and count out how many times they get 1, but they're not looking at the structure of the circuit that they're given as input. So you could hope to leverage that. Another reason PRGs are doing a harder task than they need to for the purpose of just counting is that they're actually finding satisfying assignments. And for the counting problem, we just need to come up with this estimate of the fraction of all assignments that do satisfy the function. So it's natural to ask, can we solve deterministic approximate counting faster than a PRG? And the answer turns out to be yes in some settings. A well-known example of this is the class of DNF formulas. So I don't want to go into great detail here, but if you look at the best-known running time of a deterministic approximate counter based on PRGs, you can see it's really quasi-polynomial. You've got n to the log n kind of factors. Whereas if you're willing to just settle for deterministic approximate counting and you don't actually try to cook up the full might and majesty of a PRG, much faster algorithms are known, n to the log n. So one of the takeaway messages from this talk is that we're going to see a similar in spirit phenomenon for the class of polynomial threshold functions. We'll be doing deterministic approximate counting much faster than the best known PRG-based approaches. Okay, so what is a PTF, or polynomial threshold function? It's just the sign of a real valued polynomial. So the input space is the Boolean cube. It outputs plus or minus 1 values, Boolean function. And the computation is just you evaluate some degree D polynomial for a degree D PTF and spit out plus or minus 1, depending on whether the value of P is positive or negative. Okay, and it's not too important. We only have to think about multilinear polynomials because our input domain is plus or minus 1. Okay. So there's been a lot of work on PRGs for degree D PTFs going back for close to a decade now. These are some well-known results of Mecca Zuckerman, Kane. This is work with Liang from a couple of years ago, the last row. And I don't want to go into great detail on these running times, but you can see there are different trade-offs in terms of what you can achieve. In the first entry, we have sort of this 1 over epsilon to the D dependence in the exponent. In the second entry, Kane did better. It's a fixed polynomial in 1 over epsilon, but there's kind of an Ackermann dependence here on d in the exponent. And finally, the third row is a little bit different. This is kind of a Nissan-Wigderson based type approach. It has a much worse dependence on n, right? We see n floating around up higher than we would like it to be, but a much better dependence than the other approaches on d and epsilon. And this will come back to be useful for us later when we get to our actual result. But this is just a little snapshot of what are some things that were known about PRGs for PTFs over the Boolean cube. Okay. There are also some other approaches to deterministic approximate counting. This is an old work with an India Day, but I won't really talk about this. So what I do have to talk about is PTFs over Gaussian space. And this looks like a weird, different generalized setting than the Boolean case, but we'll actually see it's a special case of Boolean PTFs. So it's very similar. Again, a PTF is just the sign of a degree D polynomial, but now the differences are highlighted in red. The domain we think of as being all of Rn, and we're interested in doing this counting, estimating the fraction of satisfying assignments under the standard Gaussian distribution over Rn. Okay, so that's the deterministic approximate counting problem over Gaussian space. It might look weird or different, but if you want to solve the Boolean problem, it turns out you provably need to be able to solve the Gaussian problem in order to do this. And why is that the case? Well, it's just because of this well-known phenomenon, bits can simulate Gaussians, right? If I have a bunch of independent bits, xi1 through xim, I can add them up, normalize suitably, and of course the binomial comes to look like the Gaussian. So I can simulate this Gaussian variable zi. And you notice that this is a very efficient simulation in terms of polynomial degree. Z is linear in the xi's, so if you have a degree D polynomial over Gaussian variables, you can really simulate it with a degree D polynomial over bits. So you can make the statement precise if you want to solve deterministic approximate counting for the hypercube, the kind of standard problem. You need to be able to solve it for the Gaussian case as well. Because of this, many researchers have looked at deterministic approximate counting for PTFs over Gaussian space. There are a bunch of results here, a couple of results by Kane. This is work which I also should have listed. Dan Kane is one of the authors. Kelly and Mecca had recent work. These are all PRG-based approaches, and they're all better than the known Boolean results. So we're really seeing this phenomenon that the Gaussian case does appear to be easier than Boolean deterministic approximate counting. Okay, whoops, too far. So this slide puts together everything we've seen so far. It summarizes the prior results on deterministic approximate counting. You can see these Boolean results, and the lines kind of show you comparable things that we can compare against each other versus these Gaussian results. We seem to be doing better pretty much in the Gaussian case, right? This is some Ackermann function of d here on the Boolean side, and it's just an exponential 2 to the d in the Gaussian setting, right? And the Boolean side here, we have like a d over epsilon to the d in the exponent. Over here, we have just a fixed polynomial in d over epsilon, okay? So the takeaway is that we're able to do better. We have more efficient algorithms for deterministic counting over Gaussian space than over Boolean space. And there's a good reason for this. We'll see the reason in the rest of the talk. Boolean results often have to do an additional step. First, they kind of prove the result for Gaussian space, but then there's some additional loss because of using a technical ingredient called a regularity lemma, and we'll talk about this. So, all right, what's this paper about? Well, the main thing that we do in this work is we came up with a more efficient way to sort of transfer Gaussian results to the Boolean setting. We have this method, it's a derandomization of the regularity lemma that lets us achieve essentially the Gaussian running times for the Boolean deterministic approximate counting problem. And we don't do it by coming up with a PRG. So this summarizes a little bit more detail. The actual quantitative results we achieved, they're probably not so central, but I would just sort of, maybe the lines help you help you see the picture. We sort of are able to leverage this good dependence on the other parameters, d and epsilon. Here you see we're not paying this like n in the exponent. We sort of get the n from over here where we like it, and the last row on the Gaussian side, and we get the d and epsilon dependencies over here where we like them, the Boolean side. You can also compare this result with this result. You can see we're basically getting the Gaussian runtime in the Boolean setting. And again, how do we do this? We do this via this derandomized regularity lemma. So in the rest of the talk, I'll tell you a little bit about this. What is a regularity lemma for PTFs? How are they useful? And what is the derandomized regularity lemma, and why is it useful for us? Okay, so let's get into it. To tell you about a regularity lemma, I have to tell you about regular polynomials. A regular polynomial is just a polynomial where no individual input variable has too much influence sort of over the overall outcome of the polynomial. It's good to think of this as like over the Boolean setting. Of course, we can think of the domain of the polynomials, the reals, but just think of it as like +1 - 1 inputs to the polynomial. So there's a well-defined notion. you can have of, this polynomial pi that's just sort of the sum of all the monomials that contain xi as a variable. You can define the influence of a polynomial. I'm not giving you very rigorous or crisp definitions here, but it can all be made quite precise, right? And again, the idea is that a regular polynomial, a polynomial is epsilon regular, if every variable only has a small fraction sort of the total influence or the total variance. So just in pictures here, you can see that a polynomial like this linear form, the sum of all n variables, is very regular. No individual variables contributing too much, whereas the polynomial p of x equals x1 is the ultra non-regular polynomial, right? That one variable x1 accounts for everything. Okay, so something you're very likely familiar with, the famous central limit theorem, or the quantitative versions due to variant SAN. These theorems say that if you have a regular linear form, so a regular degree 1 polynomial, then it doesn't really matter whether the individual inputs are bits or Gaussians. The overall distribution of the polynomial, you can make this precise by looking at the CDF distance, is essentially the same, whether the underlying input variables are Boolean or Gaussian. So you can see here in the first row, I'm summing up n bits. I'm interested in the probability the normalized sum is at least 1/3. And the central limit theorem tells me that's pretty much the same as if I'd summed up Gaussians and done the same normalization. And visually, you can just see that none of the sort of discrete lines corresponding to the binomial distribution, the sum of the bits, is very far from the sort of little curved line you can see in the background. On the other hand, if you have a non-regular polynomial like x1, then of course this is very far from true. The probability that a single bit is larger than say 1/3 is very different from the probability that a Gaussian is at least 1/3. You can see these big error regions. Okay. So that's the central limit theorem, a powerful generalization of it due to Marcel O'Donnell-Leskovich from about 15 years ago says that this is not just a phenomenon for linear polynomials, it's also true for low degree polynomials. Degree D polynomials have this same kind of behavior. It doesn't really matter if they're regular, whether you plug in bits or Gaussians. And that's kind of obviously going to be useful for connecting, fooling Gaussian PTFs and Boolean PTFs. So let's go into that in a little more detail. The invariance principle, again, this is just a quantitative statement. If you give me a polynomial that's degree D and is epsilon regular, then this is sort of a quantitative statement of, what's the difference in probability that under Gaussian inputs versus under Boolean inputs, it's likely to exceed any given threshold. And the takeaway from this is that you can assume for deterministic approximate counting, if you're working with a regular polynomial, that the inputs are Gaussian. Great, you get to solve the Gaussian problem, which is easier. So if you're really trying to solve the Boolean deterministic approximate counting problem, though, well, you have to, somehow get a result in the Boolean case. And you know now that if things were regular, you'd be in good shape. So what are you going to do? Well, basically, you hope things are regular. And if they're not, you do the obvious necessary surgery to try to make them a little more regular. So that's the substance of these PTF regularity lemmas. A number of these were proved in different works about 10 plus years ago. Kind of illustrate it with a picture. So you start with your initial polynomial P. If it's regular, then you're done, right? We know we can just pretend that the inputs are Gaussian, even though they're not. If it's not a regular polynomial, well, it's not regular because some variable's influence was too high. So what should you do? Well, you should greedily take the highest influence variable and restrict it away, set it to both possible values, and now you've got two problems to solve. You've got to handle this polynomial and this polynomial, but you got rid of this variable, which was sort of causing a lot of irregularity. So maybe now one of these polynomials is regular or closer to regular in some sense. So you can just proceed in this way, right? Keep on building the tree. If this guy was regular, you stop. Otherwise, you break it down based on its most influential variable and continue. And the substance of these PTF regularity lemmas says that this decomposition process terminates pretty efficiently and works, right? So if you want to kind of see the detailed statement, it says that there's an efficient deterministic algorithm. The algorithm's easy. You just look for these most influential variables and keep splitting as long as you're not regular. And if you feed in any degree D polynomial, this decision tree building procedure will halt. It'll output a decision tree such that almost every leaf is going to be either regular or very close to regular, like such a skewed polynomial, almost always outputting the same sign that it's also easy to handle. Okay, and there are quantitative, of course, detailed statements about the height of the tree, so on and so forth, but for our purposes, this is enough. Okay. So given this regularity lemma, you can see it's exactly the tool you need to be able to use Gaussian deterministic approximate counting algorithms for solving the Boolean problem, right? Somebody gives you a polynomial over the Boolean cube. What are you going to do? Well, if it's regular, just run the Gaussian algorithm and you'll get a good answer. If it's not regular, run this regularity lemma, right? Start constructing this decision tree. You'll get a decision tree with a bunch of leaves. Almost every leaf, you will have a regular polynomial, or else you have an easy problem to solve just some first principles. And so you just run the Gaussian algorithm at every leaf, pretending that, pretending that the inputs there are Gaussian. And we were able to control the error thanks to the invariance principle that we saw before. Okay, so again, we're happy with the Gaussian runtime cost, but the cost of this decision tree construction could be expensive. And an intuition for why it could be expensive is that it really is like a brute force procedure. We're essentially using true randomness to pick a path down the regularity lemma constructed tree. It's like enumerating over all outcomes of the randomness that defines a random path down through that tree. So if you're thinking from like a randomness, efficiency, deterministic simulation perspective, this looks like maybe there's an opportunity for savings here, and indeed there is. So this is probably the most important slide of the talk. The new approach, the contribution of this work, is that we don't sort of brute force construct the entire decision tree that the regularity lemma would construct. Instead, we use a suitable pseudo-random distribution to choose sort of cleverly selected random or pseudo-random paths down the tree. And we'll do brute force just over the seeds to that pseudo-random generator. Just will only inspect that small subset of leaves of the decision tree. So most of the regularity lemmas sort of decision tree we don't actually build or construct, and because of not doing that, we're able to achieve a big savings. That, in a nutshell, is the main idea. So I'll give you a little bit more detail. What does this mean, a suitable pseudo-random distribution, right? What does that distribution kind of correspond to computationally? Well, if you work it out, it turns out that the type of pseudo-randomness property you need to construct the right subset of the decision tree is you need a pseudo-random distribution which can fool polynomial threshold functions. They're degree D PTFs. I mean, the whole thing's a degree D polynomial. And kind of the number of variables of these PTFs that you turn out needing to fool to pseudo-randomly construct the decision tree, the number of variables corresponds to the depth of the decision tree, the depth of the tree constructed by the regularity lemma. So the intuition is that, hopefully this is a small number. This should be a small number. And if that means that if you had a PRG, which had a good, maybe a poor dependence on the number of input variables, the dimension, but a good dependence on these other parameters, then you could achieve a savings by using such a PRG to sort of pseudo-randomly select which leaves of the tree to construct. So do we have such a PRG? Indeed we do. This is what we mentioned earlier, this work with Leung from a couple of years ago. This is a PRG with a much worse dependence than all the other ones we saw on the number of input variables. Again, n is floating around up here in the exponent of the exponent in some sense, but it has a much better dependence on the error parameter epsilon and the degree D of the polynomial. So that's exactly what we leverage. So our overall approach is, we have this, just thanks to the rest of the literature, we have these efficient Gaussian algorithms for Gaussian deterministic approximate counting, and we solve the Boolean problem by constructing the decision tree. Well, that's what we don't do in this case, right? Now we're going to use a PRG for Boolean PTFs, in particular Boolean PTFs over a number of variables corresponding to the bound on the depth of that tree, to construct kind of a partial decision tree. We only build out a tiny fraction of this regularity lemma decision tree. We run the Gauss, then the rest of it is just the same. We run the Gaussian algorithm at each leaf and we combine the results, and these are the bounds we end up getting. Probably don't really want to walk you through this slide because I think it's a little bit too much detail, but it's sort of the real statement of the derandomized regularity lemma. So just to say a little bit about it, right? You need a you need a PRG for polynomial threshold functions. They're going to be PTFs over the depth of the decision tree, many variables. The crux of the theorem is that we have an efficient deterministic algorithm. It builds sort of only the skeleton, this little bit of the restriction tree. It spits out the relevant restrictions, and with high probability, almost every pseudo-randomly generated leaf in this partial tree is either going to be regular, in which case we're good, or it's going to be close to constant, the PTF there, in which case it's also easy. And the crucial property is that this is a representative sort of skeleton of the entire tree. We can just look at the leaves we get here, and it gives us a high accuracy approximation to the overall right answer. So all the details are in the paper, of course, but just to wrap up and recap, the main contribution of this work is we have this new method, a derandomized regularity lemma, which lets us kind of port Gaussian PTF, deterministic approximate counting runtimes, over to the Boolean setting. Okay, that's it. Thank you very much.